Very good. Welcome back. So we've been looking at the method of maximum entropy. And the idea here is always going to be maximize an entropy subject to constraints to find probabilities. Very good. So what I have to do now is make some general remarks about constraints, objections that have been raised to the method of maximum entropy, and how we can actually analyze those objections and think about them in order to be able not to make dumb mistakes. So how does this go? Very good. Let us get our screen there. So our issue is going to be talking about constraints and the information that the constraints codify. And the general strategy then is maximize an entropy subject to a constraint. I'm just going to put one constraint to simplify life a little bit. The constraint in the form of an expected value. And from there, we get a probability that is of the canonical form, which contains a Lagrange multiplier, lambda. So the prototypical example that we're going to be using in all of this is the situation of thermodynamic equilibrium, in which we maximize the entropy subject to an expected value of the energy, and the probability of each microstate is going to be given by the Boltzmann distribution, in which you have a Lagrange multiplier beta that contains the temperature. So the questions that arise in this type of inference process are going to be, what F do we choose? How do we know that the energy is the quantity that happens to be relevant to thermodynamic equilibrium? What is actually the expected value that we put here, and that's so necessary to figure out what the Lagrange multiplier is? And the typical question is, you're making inferences on the basis of incomplete information. So how do you ever, would you ever know that the inference is reliable at all? So that's the typical question that arises. And a number of objections have been raised to the method of maximum entropy. And so what I would like to first write down is a common formulation of what the method of maximum entropy is all about, and then poke some holes in it and figure out how we bypass all these problems. So this is the formulation that Jaynes would give usually. He would say, we want the probability distribution that reflects what we know, which is the constraints, while remaining maximally unbiased, and this means unbiased, means here maximum uncertainty or maximum entropy, about what we do not know. So what I would like to say, be very careful with statements like that. One of the common objections that's raised, and it's a very legitimate objection, is that, take for example black body spectrum, black body radiation. Then the black body spectrum is what it is independently of what we happen to know. Reality couldn't care less about what we know. Reality is what it is. On the other hand, our predictions, and physics is to a large extent about predictions, our predictions depend on what we happen to know. So what's interesting about this objection, and it was an objection that was raised in the early days of entropic inference, is that it is a legitimate objection. And how do we answer it? Or how do we understand what the problem is? the issue here is one of understanding what it is that our physical theories are meant to accomplish. What is the purpose of our theories? What are theories for? One possibility is that theories are supposed to provide models that mirror reality. If that is the case, if theories are supposed to mirror reality, then whatever information we might happen to know or not know is irrelevant. Nature doesn't care what we know. On the other hand, if the purpose of theories is to provide models that are tools for processing information for the purposes of prediction, explanation, control. So if the purpose of theories is this very pragmatic purpose of helping us cope with reality as opposed to mirror reality, then you can see that whether we happen to know something or not is highly relevant. After all, that's the only information we have. How are you going to draw conclusions or draw predictions or try to control experiments if you don't happen to have that information? So then it matters. So the objection here is a very interesting one in the sense that its solution or not depends on a decision on what our theories are for. What is the purpose of our theories? Is it to mirror reality? Or is it the more pragmatic purpose of being useful tools? How do you pick? Okay, I have two comments about this that may be relevant. One comment is, as far as any individual goes, you have to make up your mind, right? It may be that your prejudices make you lean in the direction of A, because after all, we all want to know what reality is like. On the other hand, sociology may push in a different direction. In other words, what is one A or B, which is the one that's going to succeed, depends only from a societal point of view on which is the strategy that succeeds. If strategy A does succeed, then fine, you won. On the other hand, if you find that strategy B is the one that continuously succeeds, then whether you wanted to have a picture of reality or not becomes irrelevant. These B guys are the guys who are going to get tenure. That's the way societies work. Success speaks for itself. So it all depends on what is the program A or program B, that is successful. That's one way to look at it. Another way to look at it is that it is amazing that throughout the history of science, people have really leaned in the direction of A. One tries to come up with models that mirror reality. You try to, in the words of Hawking, read the mind of God. But it is nevertheless amazing that while people were trying to mirror reality, they have come up with theories that include concepts such as probabilities and entropies and geometries, concepts that are designed for the purposes of manipulating information. So while it is true that people have attempted to pursue path A, the kind of theories that they have come up with really fit much, much more nicely in program B of theory construction. So there. So I think that this objection The black body spectrum is what it is, independently of what we know, is merely addressed by saying, now, what we know is another thing we have to go on, and that's what our theories are for. So let's proceed with another couple of objections that are also powerful. Let's read what we have here. Let's see. Let's read this formulation of the maximum entropy philosophy. We want probability distributions that reflect what we know while remaining maximally unbiased about everything else. The objection that I want to call your attention here to is that if you're going to build thermodynamics and you say, I'm going to maximize the entropy of a probability distribution with a constraint on the expected value of the energy. Well, the objection here, and this is a really legitimate objection, the expected value of the energy is not something we know. You never say, oh yeah, here I have this glass of water, its expected value happens to be 3 joules, what's the probability distribution? Nobody ever knows that. In fact, we never know the expected value of the energy. You might, if you're lucky, know the temperature, but the expected value of the energy is not something we can ever know. Maybe you can infer it from values of the temperature, but it's not something that's accessible to you. So then the question is, how can you say this? We want a probability distribution that reflects what we know. You do not know the constraint. So that's a serious objection. Another objection of the same type is, even if some expected values happen to be known, so what? You have 10 to the 23 particles. If I give you 2 or 3 expected values, why would the inferences be any good? How do you tackle the problem of, is there any reason to believe this is going to be good? Those are serious objections, and we have to be able to tackle them. So let's see how we proceed to do this. The way I'm going to handle this is I'm going to classify our constraints in 4 types that reflect different epistemological states, different states of available information. So the ideal case is one in which that the expected value of some f is the information that is relevant to your problem. And in addition to knowing that this is the information that is relevant, you also know its expected value. So here you know everything. You know what is relevant to your problem, and you know the expected value. Go ahead, maximize entropy, you're going to be fine, right? Now notice here that this issue of being relevant is actually very crucial. You have to have the constraints that are relevant to your problem. If you have something like, in the case of thermal equilibrium, you have something like the expected value of the energy, and you know what it is, this is highly relevant information for some problems, but not for others. It is very relevant information to be able to figure out what the temperature of the system is. It's very relevant information to be able to tell you if 2 systems are in thermal equilibrium with each other, or if 2 systems will be in thermal equilibrium with each other or not. The temperatures have to match, right? So for some questions, this is very relevant information. For some other questions, exactly the same system, it's obviously completely incomplete and irrelevant information. If I were to ask you, what is the position of that proverbial particle number 237? Well, just knowing the expected value of the energy of the gas doesn't tell you anything. The particle could be anywhere within the box. The distribution is as broad as allowed by the container. So being relevant or not is crucial here. Very good. So that's the ideal case. For your purposes, you have the relevant information and you know the expected value. Now, most of the time, you don't have these pieces of information. So the important case, the next epistemic situation that that we encounter, and I called it the important case because it's the one that is the one in which we encounter most of the time and we can make good progress, is that we know that f is relevant, but we do not know the value, the expected value. So for example, an example of this is for thermal equilibrium, you want to know the expected value. That is the quantity you need to know for the problems of thermal equilibrium. However, the expected value is actually not known. Now, that's exactly the case that I was addressing, the objection 02 that I was addressing previously. How can you maximize an entropy subject to something you don't know when you don't know it? Well, the thing here is that the fact that you know that this F is relevant is already really valuable information, even if the actual numerical value is not known. So the way one proceeds in these cases is you say, of all the possible probability distributions, this constraint, you apply the constraint as if you knew what the expected value was. This constraint helps you to restrict yourself to probability distributions of the Boltzmann type. Where now, because you do not know the expected value, lambda remains a free parameter. So now what the method is telling you here is, look, you do not know what the numerical value of f is, but you still can use this piece of information that f is relevant to restrict yourself from all the probability distributions to a subset, the subset that takes this exponential form. And what then? Well, now you have to actually go and ask your friend experimentalist more information about what the actual value of the temperature is going to be. You need to have that. So then you proceed to seek the information that's still missing. And there are a number of ways you can do this. If F here were the expected value of the energy, then beta 1 over kT, which remains a free parameter, needs to be known. One possibility is you take your system, stick a thermometer in it, and figure out the temperature. You measure it. That's one possibility. Another possibility is, well, how about if you measure the energy of different molecules? And so you collect data. And from the energy, the distribution of energies that you get, you use Bayes' theorem, and from that, you figure out what the temperature is. So either case, you can see that this is the important case in the sense that it is the usual situation that happens to confront us for the purposes of doing physics. We know that something is relevant, but we do not know the expected value. So you proceed, find out an interesting family of probability distributions, and then you seek the additional information from somewhere else. Now there is another case. This is the case that Jaynes analyzed in some detail. This is the case that Jaynes called the predictive case. In this situation, we do not know if this expected value happens to be relevant. It's just a function that somebody pulled out of a hat. But we do know what the actual numerical value is. Under these circumstances, you can still restrict yourself to probabilities of this form. You can still restrict to this, and you say, well, this is much better than not knowing anything at all about the probabilities. We can actually make predictions. Whether the prediction is going to be good or not is something that requires some further analysis, but you can still say that whether the prediction is good or not, this gives the best predictions because it takes into account something that we happen to know. So best does not mean good. It just means any other prediction you could have made without taking this into account would necessarily be worse. Basically, the way you proceed next is to say, look, I want to figure out the answer to a particular question. If the probability distribution for that particular question on the basis of this information gives you something that's very narrow, you say, oh, this turned out to be very relevant for that particular question. So you have an expected value and you have a very narrow variance, you're in good shape. On the other hand, for some other questions, maybe this quantity happens to be rather irrelevant, like the position of a particle in a box. In that case, the predictions are the best you can do, but they're not good. Very good. Then there is the last case, which is the case of extreme ignorance, in which you know neither whether f is relevant, nor you know its value. Why do we even include such a thing? You know nothing. Well, it's because many times when people use the method of maximum entropy, they really are land in this D case of extreme ignorance. Then the method of maximum entropy gives them complete garbage, and they blame the method of maximum entropy. You shouldn't do that. If you do not know anything, the method can't help you very much. So you have to really be aware of what are the limitations of the method. The method of maximum entropy cannot help you if you supply wrong information, for example. Or the method of maximum entropy cannot help you if you supply information that is not relevant to your problem. So you have to understand that these methods are tools, and if you don't use them properly, they're not going to be very useful. The metaphor that Jaynes used was to say, look, maximum entropy is like a power tool. If you know how to use it, you can build beautiful furniture. If you do not know how to use it, you're going to end up sawing your thumb off. Be careful. Very good. One last comment about pitfalls that it's very, very easy to fall into if you do not know what you're doing. Suppose what we want to maximize entropy subject to a constraint on some expected value, and the problem is that you do not know what the value is. So one of the things that people do, which is somewhat dangerous, is to say, I do not know what the expected value is. I'm going to replace it by a sample average. You have to be very careful with that because those two things are not the same. So suppose that you have data. So you say, well, I do not know what the expected value is. I'm going to collect data. Here's the data. The data is you collect a bunch of quantities like that, and then you say the expected value of x is replaced by its average. So what you see here, this is the sample. You took a sample and then you average. This is an expected value. This is not true. right? It may be that the expected value is close to the sample average when you have a very large number of measurements, and so one converges to the other in probability, right? When n is sufficiently large, right? But you have to be careful, because if n is not large, then this doesn't work. So being large, that would be okay. But now let me show you another aspect of this that's sort of like amusing. How do we know what f is? This is a big mistake that sometimes is made. If you have collected data like that, it is tempting to put f equals the function x. And in that case, you say, okay, let me put x equals 1 over n. So two mistakes here, right? Two mistakes. One of them is this is not true. But suppose that n is large. Okay, for large n. So the question is, why do we choose the function f equals x? Because you happen to know the x, right? Because we know x1, xn. But notice the trick here, that the flaw in reasoning that has been introduced very surreptitiously. But when you know x1, x2, xn, we also know x1 squared, x2 squared, xn squared. The moment you measure x, not only you know x squared, and you know x cubed, and you know any function of g. So why not introduce a constraint on the function g and set this 1 over n gx alpha to n? Why not introduce a constraint of this form? In fact, why not introduce a constraint that involves x, another one that involves a squared, another cubed, another g, and then any other function you might want? You see what the problem is? When you try to say, oh, I have data, I'm going to maximize the entropy subject to that data, you have no idea about what the function, whether the function f is relevant or not, and you have no idea about what the expected value is going to be. So don't do it. You just have no way to, just from having data, you have no way to actually make the assessment that this is information that can be processed using Shannon's entropy. So this doesn't lead anywhere. The maximum entropy method can handle expected values, but it cannot handle sample averages. Thank you. See you next time.